So before the break, we looked at the CMC. So now we look at the application. So you have a metal matrix composite made of boron, fiber, and you know that fiber, aluminum alloy. To form the boron fiber, tungsten wire R10 micron was coated with boron, given a final radius of 75 micrometer. So if you look at this diagram, so you have boron and tungsten. So you have boron and tungsten, okay? So final radius 75. So this is diameter, diameter, this is radius, so actually the same thing. The aluminum alloy is then bonded around the boron fiber, given volume fraction of 0.65 for the aluminum alloy. Assume the rules of binary mixture also apply. So binary mixture means the one that we learned before the break. Also to the ternary mixture, calculate the effective tensile elastic modulus of the composite under isostrain condition. So it gives you under isostrain. So isostrain is the one that we learned. You have isostrain and isostress. Isostrain is the one that before last week, last lecture. So data, EW, you have something, EB, you have something, E aluminum, you have something. So you need to find, the question asks you to find calculate the effective tensile elastic modulus for the composite. So you have fiber, aluminum, and boron reinforced with aluminum alloy. So you have basically you have two fiber and matrix. Okay, you have fiber and matrix. Only now the fiber have two things. You have aluminum plus boron. Okay, aluminum and boron. Okay, right. Now you use the binary mixture rules, where on the left hand side always the complete elastic modulus composite. Then on the right hand side is the fraction, what you have. So in this case, you have tungsten or W, you have boron, you have aluminum. So you do the same calculation like you learned previously. Now you just add one more component, because this one is you have three elements. You have tungsten, you have boron, you have aluminum. Okay, so you know from the statement here, there's a combination between boron and wire. Boron and tungsten. So boron and tungsten is 0.75. How you find 0.75? Because the aluminum alloy here, it gives you volume fraction 0.5. So the whole composite is 1. So now you have the aluminum alloy is 0.6. So the boron and the tungsten will be the 0.35. Make sense, huh? Make sense, huh? Okay. So aluminum will be 0.65. Now you start to calculate the fraction of the wire. This is a combination between two. So you need to find within this 0.5, how many is tungsten, how many is boron. In the question, it gives you some information to calculate, which is the radius of fiber, B fiber, and W wire. Right? You have W wire is 10 micron, so diameter is 20. So you have, and then coated with boron with 75 radius or 150 micron diameter. Okay, so from here you can calculate the B and W, the area, right? The area fraction. So if you cut this one, you should able to see the W area and B area. So you take W over area of B multiplied by the fraction of 0.35. Yeah, so means you take the bigger circle, the total area, and then you want to find fraction of W, right? So you calculate the W over or divide over the total area you have. Then you get the fraction, right? So this is another further calculation. In short, you can just use pi r square divided by pi r square of W and B. This is just a bit longer steps because you just want to put everything in the same language or same things. So here, you just take how you calculate W, you take B minus W divided by W. What else? And fraction of W equal to, same lah. So yeah, so like what I say, straight away use pi r square for the area. Then the fraction of W will be 6 point something 10 power negative 3 dimensionless. Right? Very, very small, very, very small. Then the FB, actually FB, you just take this one minus this one. Okay, take this one minus this one. Or you want to go for long calculation, you can take area B minus area W divided by area B also can. Okay, also can. All right. So you get 0.34. Okay, 444 something. Okay. So once you get FB, FW, then you can calculate already. You can find this one, you find this one. This one was given. So this value was given, this value was given, this value was given. Substitute and you get the final elastic composite value. Okay, makes sense. Okay, try to understand the principle behind. Okay. Okay. So once you get your EC. Okay, so let's say that we change the question a little bit. So again, no picture, no everything, but it tell you metal metric composite. Metal metric composite, it make of volume now, 80% volume aluminum and 20% SCI whisker. Density given, density of aluminum alloy given, and the whiskers is given. So now you're given density. Calculate average density of the composite. Same like what I write on the whiteboard here. You change the P into whatever you want to calculate, right? So here you just change a little bit. You just assume you have 1 meter cube of material. Then if you have 1 meter cube, then you have 0.8 meter cube of aluminum alloy, 0.2% of CI fiber, right? So this is 20%, 80%. So it's just from 1 meter cube, how many you have. Why you need meter cube? Because it given you density. Okay, so mass of something, you take density multiplied by the volume, you get the mass. You do the same for viscous, you do the same. Then you have the total mass already. Once you get total mass, you can get the fraction. Okay, the important, you want to get the fraction, the VF or the MF, right? So average density, you take mass divided by the unit volume. In this case, the mass of the total composite is 2 point something divided by 1 because we assume 1. So the average density will be 2.84 megagram over meter cube. Okay, so the first step here, you assume 1 meter cube, you find the fraction. of the volume. From the volume, you calculate mass. You add up the total mass you have in 1 meter cube. Then from 1 meter cube of weight, you can convert this information into density. Okay, into density. So from here, so this is the more direct one. Actually, this one is the question might look very complex, but sometimes the step is very simple. Okay, so this one it asks you the average density of the composite. All right, the next one, this one is more application. So same, now you have a Si glass ceramic fiber, and you have again here you have the ratio, right? The diameter and the area. So same like your example number 7. You find the ratio of area of that particular things divided by something, then you calculate. So this is a ceramic matrix. You have a Si fiber embedded in ceramic glass. The question asks you to calculate the tensile elastic modulus E of the composite under iso strain. This is iso strain, so use the previous one, the equation. But what I write on the whiteboard here, you just change the P parameter, right? So calculate the stress strain at which crack start to grow. So crack start to grow, you need to use a KIC value already. KIC value. So KIC value was given, or if you see the question, you start to see KIC means you need to calculate crack already, or defect already. Okay. So how you calculate? You use the binary equation. E equal to, you have two type of material here, ceramic and SCI. So the first component is glass ceramic GC, SCI and SCI. So you have two component here. The fraction you calculate based on the area. Here you have area. You can calculate area, right? So this is just show you how to find the area. So area of fiber divided by total area, you get the SCI and so on. So here pi r square. The R here again, don't confuse between radius and diameter, because when you do in your assessment, you might panic already and then you use the wrong parameter. Okay, so just be careful. Okay, this one I straight away use pi r square, so 25 diameter. Okay, so you have a SCI fraction, the fraction of the SCI 0.73. So again, once you have SCI, you know lah, another one will be 1 minus this one, right? Okay. So you have FGC, FCI, E is given, substitute here. Then you find the isostrain condition modulus Young for the composite. Okay, the answer will be 172 gigapascal. Okay, for your assessment and final exam, please give minimum 2 decimal place, maximum 3 decimal place. Okay, with the unit. Without unit, 50% discount for the answer. If this one costs you 3 marks, you only get 1 point, 1 marks. There's no 0.5 marks in my marking. Either you get full marks or lesser mark. Okay. Right. Then you calculate the stress for the crack to start in isostrain. Again, isostrain means the deformation is the same. So the equation you use is strain composite equal to strain. The fiber or matrix will be the same. In this case, you have the two component, matrix and fiber will be the same. Right? Recall Hooke's law. Again, Hooke's law is still very important. Stress equal to modulus Young or elasticity modulus and strain. So you rewrite or rearrange this equation, strain into stress and E. Why stress and E? Because the question gives you E. You cannot use strain, you cannot use strain. You can only play with the information you have. So you modify a little bit by using Hooke's law. So your equation becomes stress divided by E. Again, this is isostrain and not isostress. Isostress, then all this will be the same. This is isostrain. And before we learn about defect, we learned that stress equal to KIC divided by square root of pi a. We learned this equation before. Right? KIC equal to stress multiplied by square root of pi a. We learned this equation before, the equation for KIC. So you rearrange the KIC equation, stress equal to KIC divided by square root of pi a. Again, what is A? A is a crack length. So again, crack have two types. Crack have two types. One is at the edge. One is internal crack. Internal crack is 2A. And you're using half to use calculation. This KIC is using this A, but when you answer the question for internal crack, you need to multiply by 2. Okay. So you substitute. So the stress here for ceramic material largest free-axis flaw is 10 micron in diameter. Free-axis flaw. Does it give you? Yeah. So in the question, it gives you free-axis flaw for matrix is 10 micron. However, fiber is only 5. So if you have a free-axis flaw for 10 micron, so you divide by 2, your A will be 5 micron. This is internal flaws. Right? So here is the internal flaws. This 10 equal to 2A. So your A value to calculate for this equation over here, you use 5 micron and not 10 micron. Okay. So you substitute inside the equation. Okay. You substitute inside the equation. Here you copy. Here you copy. Then you change to, okay, this one you change a little bit because okay, KIC. Okay, you change the stress for ceramic. See, I missed out something in my calculation. This one should be one set for GC, one set for the SIC. Okay. This one, I think there's a typo error here. It should be GC. Okay, it should be GC. Then you substitute your A5 for glass ceramic. This one. Okay, typo error in my slides, not SIC for the second one. So from here you find the composite stress. Okay. So here you need to calculate. There's a steps that I skipped already. So you need to calculate for ceramic matrix, you do one time and then you do for another one. Then you compare the results. So this one I do for the first one, plus ceramic. Again, typo error on my slides. This one should be following this one. This one should be here because you substitute this one with this equation. And you are using 5 micron for ceramic matrix. Okay. You do the same for SIC, but SIC now, this is a surface notch. Surface notch is 5, so your A is 5. Surface notch is this one. This is H. This is surface. This H defect A. Yeah. So 3/6 floor in diameter is this one. It tell you in diameter, so it's internal flaws. It's 2A. So basically, the 2A is the same lah. Can you see? Actually, the 2A is the same. A is the same. I mean, the A value is the same. You can see, one is 3/axis floor in diameter with 2A. You divide by 2, you get 5. For SIC is 5 micron, but it still use back the 5 micron in the calculation. So basically, the two equation here is the same. Right? All right. So you still get the same answer. So at the end, you get 1109 megapascal. Make sense, Make sense, Okay. Okay, silicon fiber, you do the same. What is different here is the K value, the KIC value. Okay. So you have two. One is 5,9 something, and then for glass ceramic is 1,000 something, almost 1 time bigger. KIC. So SIC fiber in the ceramic will begin to crack first when you apply force of 596 megapascal. Makes sense. So you have two value KIC you calculate, then the stress that can handle by ceramic is 1109. But stress that can handle by SIC fiber only 500 something. So if the two object was stressed at the same time, so of course the lower one will fail first. Right, lower value will fail first. So SIC fiber will fail and crack will propagate first. Right? Okay. Okay, we go for the last example. This one important for final exam. Yeah, for final exam. Yeah, tell your friend. Just now we go up. Tell your friend. Okay, so this is a design question. So you have a composite shaft designed to have outer diameter 70, diameter so and so, length so and so, and then you are given some customer requirement. Mechanical properties is important, is bending stiffness. So you need to recall back in your, I think, statics that you learn bending. So this one is linked with the statics. So bending stiffness in terms of longitudinal modulus, blah, blah, blah. Stiffness is to specific maximum allowable deflection bending, subject to 3-point bending. There's one more figures. So support point, load 1000 Newton is to produce a plastic deflection not more than 0.35 at the midpoint position. Okay. So okay, so this is another diagram that is support. So So this is a diffraction. This is a diffraction question. So you have a shape that this one, and then it deflect under loading 1000 load. It will deflect something like this. And then there's an equation that you learn in your static stress equal to mc divided by I. So all this equation was given, right? So if you have a rectangular shape, then you use all this formula. If you're a circular shape, you use all this formula, right? Now, again, this example is important for your final. This formula will not be given. This we assume you already know, and because you already passed you're doing your static now, is it? Okay. So again, we assume you already know. We assume you already know. So you prepare this one, you prepare. You write somewhere, before you go in the exam hall, memorize this one, at least you write somewhere. It's not given, it's not given. Yeah, but you'll see something like this in one of the questions. Okay. Exam question final, you have 5 questions, 3 compulsory, 2 optional. This is one of the optional questions. Yeah, this will be the one of the optional question. So it's a very long question. So you have polymer fiber oriented parallel to the tube axis is used. Possible material was given, glass, carbon, intermediate grades given, epoxy is given, and so and so. So you're given a table in the question, all the material that you can use, the properties, and the cost. It's a design question, it's a long question. It will take you like, maybe you need to use the full 30 minutes just to solve this one question. So the design caused us to do the following: decide which of the 4 fiber material can be used to support the customer requirement. Out of possibilities, select one of the fiber material that will yield the lowest cost of a composite material. So it will be similar to the one you see in your test 1, right? The test 1, the second question is similar things. They give you a customer requirement, then you choose which one, right? So what are the customer requirement? Is stiffness is to be specific allowable bending, so you need to calculate the maximum bending, deflection, and then under this load, and not produce more than 0.5. So you have load, you have a maximum, cannot more than this deflection in the midpoint location, and you need to use the one that you learn, I think, in your physics, your bending motion. I don't know whether your static lecturer got teach, right? That's another matter That's another matter. But you should learn. You should learn. You should already know by now You should know by now. So so to support, and then there's one force at the middle, and there's an equation to use. Stress to calculate this kind of deformation is use mc divided by I. So there are mci stress value here. Okay, so it depends on the shape that you have. The shape we have is a cylindrical. So we are using this equation. So the moment that create in this setting, you use FL divided by 4, because the question gives you the length already. So by the force is 1000 Newton. C is the R. R is the radius, the radius of the tube. Okay. Then the the I here, I is given a pi r square, pi r power 4 divided by 4. Then the stress is FL divided by pi r cube. Okay, all following these slides here. Standard already. So if a bending question come out in static, then you expect you to know the same thing also. If come out Okay, so we apply the equation. So if you want to calculate the computation 3-point deflection you need to use this equation. Delta y equal to FL cubed divided by 45 EI. This one is a 3-point bending. 3-point bending. So deflection given by maximum y equal to this equation. And you need to calculate the cross-section moment of inertia. Moment of inertia is, for dynamics, there's a table you follow. So static, I'm not sure lah. I think static also will give you also. So since we have a hollow tube, this is a hollow tube. So hollow tube, you take the outer shape minus the inner shape, you get this hollow shape. That's why in this equation, you see this one. So how you get to this one? Actually, there's a formula. There's a formula. If you study dynamics, you will see this table. Okay, the second moment things is the same. So maybe Patrick can teach you guys how to use this one. So it's the same. It's the same. You refer to table straight away. You use the formula, right? So this is the first one minus the second one. Okay, so you rearrange the equation. Okay, you put in. You want to find the E, right? So you rearrange the equation. Y you put inside here. Pull out the E, and then the I equal to this full length equation. You just substitute inside here the I. Rearrange, you get this one. Okay, now the important equation here is this one and this one, and the one that you see in these slides. Okay, so once you substitute, you have all the parameter. This is the one that you need to design, right? So you have all the parameter here. 1000 maximum length, maximum yield, maximum deformation in the center is 0.5. DO, DI. DO means outer, DI means inner. So you use these two equations, rearrange, you find the E that you need. Why you find the E you need? Because the question give you this table. So you based on the table information, you find what information that you can extract from the question. So here is the modulus E, the capital E. So you try to think like, okay, this is a 3-point bending, what formula I have, right? So based on these two equations, you substitute, right? You get your E value is 69. You substitute everything here. At the end, you get one number. So based on this number, you see from the table which one is the correct one. Okay, next step is to determine the fiber matrix volume fraction for each of the 4 candidates fiber. It's a long process, but you try to understand the steps. You get the E already. This is the composite E that you need. Then you are given a table. You have lots of choice, so you use this equation. Use this equation to put in the combination. It's a lengthy process. It's like the one that you see in your test one. Okay, so you use this equation that you see since the beginning. EC equal to EM the matrix plus the fiber. Right. So you put in there. You put in the ratio. Right. Put in the ratio. Then you calculate. Right. So this one is the after you compute. This one you need to use inside here. So there are only 3 carbon fiber that is possible because their VF value is less than 0.6. VF 0.6. Why 0.6? Okay, why 0.6? Because if you see, there's a customer requirement there. Okay, this is your calculated value, the calculated value from here, right? You get the value of VF, you transform this one, you change this one to VF or VM, these two, you put into one term, then you will find one of the value first, then you will find another one, because this one, if you find VF, you can find VM. 1 minus this value equal to this one. Or this one, 1 minus this one equal to this one, same. Okay. So once you find all this to get the modulus of 69.3, which is here. I think somewhere required you to use value 0.6. Forget where it is. Yeah. The customer requirement here got mentioned. The allowable fraction for fiber is 0.6. The customer got say your fiber that you can use cannot more than 60%. So when you calculate, you based on this one, you based on your calculation, based on this calculation, when you calculate, you build a new table for the type of fiber you have. This calculation here will give you one set of VF. Then from here, you build another column with this 1 minus this value, you get VM. Okay. Then you back to the customer requirement, cannot more than 0.6. So you cancel this one. So you only have 1, 2, 3. Yeah. Then the second part is about cost. Cost linked with the volume, right? So if you you link with the initial table here, cost per kilogram. Per kilogram, you have the density, right? You can calculate the volume of that composite. You have fiber and fiber and a matrix. So when you combine fiber and matrix, you can multiply here. Let's say you have this. You have the fiber and the matrix one. So fiber percentage, you have this one density ma. So you just multiply the density and the volume, then multiply by the cost, you will get the costing per kilogram. It's a design question, right? So a bit lengthy. So the total volume of the tube, this one you can calculate the pi r square, not multiply by the length, right? The big circle minus the small circle. So the VC here is 188 something in cm cube. Then you take this one, you convert to density. Take this, convert to density, right? So your fiber, if you do the calculation, based on fiber volume, because this one, because this VC, you can find the VC, but from here you can have a VF already. So VF, you can multiply you can calculate the volume. Okay, and you can find all the parameter outside. Okay. Now, for example, standard modulus, if you take carbon standard modulus 0.29, you multiply 1885, do you get 552? You get 552, right? Can you press calculator? You take 0.293 multiplied by 1885, you get 552, right? So you just focus on the fiber based on the value you calculate. So this one you multiply by the volume, you get the volume for fiber. Then in the chart just now, you have a fiber per kilogram. So you multiply by the density, you get the weight, multiply by the cost per kilogram, you get so and so lah. You get so and so lah. So you get for fiber, you do one set for fiber, then you do one set for matrix. How you get 1333? You take 0.707 multiplied by 1885, you get 1333. Same, you calculate the mass by multiply by volume multiplied by the density. You get the cost. You combine fiber and matrix together, 59.6, 9.1, you get 68.7. You do for another two set, you can make decision already. Because these three are suitable for all the mechanical properties, this table tells you on the costing side which one to choose in the lower cost, because you work in a business world, cost is everything. So in this case, very straightforward, the lowest cost is carbon standard modulus. Fiber type, you use this one. Okay. Okay. You'll still use the same formula if you go to working or you do your internship later, if you work in the fiberglass company or so on. Okay, so this is how you do your analysis. Yeah. So with this, we conclude chapter 10. Yeah.